To recap, we're looking at functions, which are this kind of mathematical abstraction or gadget, which allows us to think about relationships between different quantities. And the main thing you should think about functions, it's a bit like a machine where you have an input and an output, and every input is a number, and it's a number that's in something called the domain of the function, which are the allowed inputs. And for each input, so for each x in the domain, there is a single output f of x, which is a number. Okay, so I want to think about the different ways we've represented functions, and there are four basic ones we've looked at. The first was verbal, the second was table, third was with a formula, and the fourth was a graph. So each of them had their own advantages and disadvantages, but what I want to do now is to think about how they all kind of fit together, or like different reasons that some of them are good and some of them are bad. So properties and relationships, let's say. Properties and relationships. Between different representations. All right. So let's basically do some boxes. Let's do 4 boxes, one for each of my different representations. So I don't know how much space I'm going to need. We'll see. Something like this, maybe. Yeah, something like that. So I want to kind of draw a nice little diagram which is going to represent how they all fit together. Okay, so in the top one, let's do the top left-hand side, let's do vertical. Oh, sorry, let's do verbal. So this is where we describe a function just using words. So this is succinct. It can be very good for simple functions or functions which are not inherently terribly mathematical. So maybe you're talking about a temperature at a given moment in time or an air pressure at a given height above sea level. But in terms of kind of the finer details of functions, verbal descriptions aren't so good. In particular, if we're thinking about domains and ranges, these kind of most basic aspects of a function. Well, the problem with both of these is it really depends on the exact nature of the function. So verbally, it's generally not at all clear. So both potentially pretty unclear. If I just give you a verbal description, I don't think it's going to be terribly obvious what the domain and range are in general. So then, of course, we could give a table. It's another way to do it. That's a pretty solid way to do things. But again, it's pretty restrictive. If I'm talking about domains and ranges, then, well, generally it's far too limited because a table can only give me a finite amount of data. So generally the table is too limited to compute these. Too limited to compute. So if we were talking about the function where it's f of x is equal to x squared, so you're squaring a number, I mean, with a table you'd only ever have finite information in it, which couldn't possibly capture the whole function because, well, you can square any number, the domain is infinite. So the table's pretty good for some things, but not great for everything. Next, formula. So this is a very powerful way to do it because we have a kind of a very crisp description of what the function is doing. But again, it could be pretty challenging to determine the domains and ranges. That's pretty opaque. It might be okay, and we'll have to get practice in dealing with these, but really, more than anything else, it requires careful algebra to do these. So the domain especially, I mean both, they require careful algebra, as we're going to see. And as I've said before, the range generally is more challenging to compute. More challenging. The domain is not easy at all, but the range, generally speaking, is harder. Finally, the graph, which I think is an extremely useful way to visualize or to represent a function. So same story, domain and range basically are very clear from this. Maybe you don't have a precise description of them, but you can really see what they vaguely look like. So generally visually clear. I'm going to do an example in a second. So from the graph, you should really be able to read off almost immediately, or at least see what the domain is and what the range is. So I want to talk a little bit about the relationships between these, because it's important to go between them potentially, especially if you're doing science, right? So if you have a description of some experiment, right, a description of a function potentially, you've got to know why it would be good to convert it into a table, for example. So the reason going from verbal to the table approach would be good would be because you'd be able to get precise numerical values. Saying your function is a temperature at a given moment in time is far too abstract, right? It's too broad. If you really want to know what the temperature is at a given moment in time, the verbal description is useless. You need a table. So this is useful to understand precise numerical values. Okay. Similarly, if you can take a verbal description and turn it into a formula, that's an incredibly good plan, because that really tightens things up. So this isn't always possible, I should add, but if possible, because, I mean, if I give you the graph, which is, as I said, the temperature at a given moment in time, there's not going to be some succinct formula for that, not unless the stars align. But in general, it won't be given by some sort of neat algebraic formula. So this is useful to make the description more precise. It just makes things incredibly precise. So this makes so useful to make the description more precise. Okay, so this is just a good plan in general. Having a crisp description using algebra or other kind of core functions, as we're going to see, is just a fantastically good plan. So let's go up to the table now. Now, if I give you a table, it would be useful to convert that table into a graph in many ways, because it allows you to kind of visually see important properties of the function. We've not covered very many so far, but it's a really good plan. So this is useful to understand kind of broad properties of the function, like is it positive, all sorts of things. So it's a good plan in general. It makes things more visually digestible, I think, right? Just a big table of numbers. Most people kind of recoil when they see that. So next, let's think about formulas. If I give you a table, there's no real way to go to a formula, not in general, right? It's too limited information. But if I give you a formula, which is probably the most powerful of all when it comes down to it, if I give you a formula, of course, I can build a table from it. And the reason you want to do that is it's exactly the same as before. It's useful for giving precise. It's exactly the same as the reason you'd switch from a verbal description to a table. So exactly the same story. Right? Useful to understand precise numerical values. And again, going to a graph from a formula, same story as a table. The formula is very powerful, but it's not easy to kind of immediately determine information. It would be a little bit like, how should I put this? I mean, if I map someone's genome, for example, right? You look at their genetic data, right? So in theory, that completely describes them in a sense, okay? Or at least how they came to be, that kind of thing. So your genetics tell you a huge amount about you, right? But at the same time, you can't just look at the tape of the genetic code and be like, oh yes, this person is so-and-so, right? You need to kind of see what they look like. And that's kind of what the graph is. The graph gives you an immediate visual interpretation of something. So this is why it's very useful. So the formula is just incredibly precise and really captures exactly what the function is, but it may make it quite opaque, right? You can't just read off everything from the genetic code, not easily anyway. So it's the same basic issue as going from a table to a graph. It makes it much more obvious kind of what the basic behaviors are. So let's do an example of this, shall we? I want to do an example of the last one, this formula to a graph, just to illustrate how incredibly useful it is switching to a graph from a formula. And graphing functions from formulas is a difficult skill, right? It's not something we're going to look at all, really. Well, actually, that's not quite true. We are going to look at it to some extent, but only for very specific examples that we're going to go through in kind of a lot of detail. To be able to really graph formulas or functions coming from formulas cold, you need to develop the skills of calculus. So we're going to talk quite broadly about things and not go into that level of detail. But let's take this kind of bottom example. Okay, so I want to show an example of this going on. I want to show an example of this. So switching from a formula to a graph and showing you why it's such a good plan. So I'll give you quite a difficult one. Let's take the, I'll keep everything quite small so we've got plenty of room. Let's take f of x is given by, I'm going to give you a piecewise function. So this is me describing it, and it'll depend on the exact nature of the input, what I get out. So it'll be x squared if, let's say, x is between -1 and 1. And strictly less than 1. And it'll be x plus 2 if, what we'll do, x is greater than or equal to 1. So if I take the time to graph this, what does it look like? Well, this is two examples of incredibly core functions. One of them is x squared, so it's this kind of upside down u thing. We're going to study this in more detail when we look at quadratic equations or quadratic functions. And then x plus 2 is kind of a linear polynomial expression. We're going to look at that in more detail too. But the main thing is it's linear, it's a straight line. So this is kind of jumping ahead a little bit for these graphs. But the bottom line is we have two graphs that we're pasting together. And what matters is we have kind of a piecewise description, don't we? So we've got kind of x-axis, y-axis. Okay, so between -1 and 1, we are y is equal to x squared. So that's this kind of parabola business. So what does that look like? In fact, let me get this a bit nicer. Should be a little bit more roughly, okay? So let's do this. Okay, so kind of curves up like this. Do a bit of a better job. Curves up like this. How annoying. Curves up like this. And the same on the other side. Curves up like this. So they should kind of be exactly the same, mirror images of each other. It's not the best picture ever. Next, let's be very careful about the endpoints. So less than or equal to -1 here. So we should have a solid dot there. just like we did when we had interval notation, to represent the fact that is in the graph. Here, you don't want to include it, so I'm going to have a hollow dot because it's strictly less than 1. Now what happens then is after 1, the whole thing switches to y is equal to x plus 2. So that's a straight line, and it would actually jump up. It would jump up to here, solid, and go off like this. Dot, dot, dot. So let's take a moment to think about everything. So this is the graph. Okay, so this is the graph of these two things. Now, it's a bit of a weird graph because of this giant jump, but can I read off things like the domain and the range from this? So the domain is going to be all positions x. So let's do it with kind of a vertical line. It's all positions x where this vertical line crosses the graph or touches the graph or intersects with it, right? So nothing over here, right? Nothing over here, so nothing's included in the domain. -1 it starts. -1 is included. It's all good until I hit 1, and then something strange happens. But at 1, it's still fine because I'm intersecting the top. And then after that, it's totally fine. So I can see all the inputs. It's just every single x from -1 onwards inclusive. So I'm going to represent that in the kind of the x-axis with this. So let's take a dot. So the domain is this guy. Dot, dot, dot forever. So I could read that off, right, by looking at the x-coordinates of the points in the curve. Now, what about the range? Can I read that off fairly painlessly? So let's mark a few important points. So I can see a few. One of them certainly is this position here. So let me just make this the same. This position here, this shared height of these guys, that happens at 1. 1 squared is equal to 1, -1 squared is equal to 1. But then I jump up to 3 here. Okay, now I jump to 3 because 1 plus 2 is equal to 3. So that's why there's this kind of jump in the story. So now what's the range? Well, the range is the outputs. And the outputs correspond to y coordinates. So let's draw a horizontal line, shall we? Because that's going to represent different y values. And think about what the range has to be. So if at any point this crosses the graph or touches it, that y coordinate has to be in the graph, right? For example, here, if I'm down there, then if I feed in that x, I get this value for y. Okay, I get that output. So I need to kind of think carefully about when this happens. So down here, nothing. From 0 to 1, so these should be exactly the same height, so they're a bit off. From 0 to 1, I'm crossing, it's all good, I get outputs. But then there's a gap. Right, I've got nothing here until I hit 3. And then at 3, forevermore, I'm hitting. So it's interesting, the range is split into kind of 2 pieces. And let's carefully mark them. I'll do these in green. So the range would be solid at the bottom, up to 1 solid, and then from 3 solid, dot, 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 from that point on. So let's kind of just capture both of these more precisely in interval notation. The domain. See, I think you could easily read the domain just from the formula here. Basically, it's telling you what the allowable inputs are. But the domain is equal to, well, it's -1 onwards, inclusive of -1. But now the range, much more interesting. So the range, which is in green, give myself a little bit more room. So it's a union of 2 intervals. It's 0 to 1 at the bottom. And then from 3 onwards, inclusive of 3. So especially the range, right? The range is very difficult to spot just from the formula. Very difficult. Domain's not so difficult, but the range really is. So this is just a really good example to give you a pretty nasty looking function, one that's defined piecewise, and just to show you the power of switching to a graph. See, if I took this and I switched to a table, I would never have all this information. You see, the graph kind of contains everything essentially. So, good example, really illustrates why graphs are so important. And I think you should always basically be thinking about graphs when you're thinking about functions, because it's such a powerful way to visualize things.